Hello, you're welcome to our physics class. Today we shall be looking at the topic specific heat capacity. Now when we talk about specific heat capacity, we'll be looking at heat first. Heat can do work. For instance, if you boil water in a pot, the heat from the fire is capable of causing the molecules of water to be in motion. And after some time, the water boils, and when it boils, it produces steam, which is capable of carrying the cover of the pot. And heat is the quantity of internal energy that a body contains. The quantity of heat received by a body is proportional to the mass and temperature change of that body. Now what do I mean? We are saying that the quantity of heat that is being supplied to a body is proportional to the mass that's receiving the heat and the temperature change. Temperature change is written as delta theta, and delta theta itself could be theta 2 minus theta 1. Theta 1 is the initial temperature of the body before the heat was supplied, while the theta 2 is the final temperature after which the heat has been applied to the body. Heat causes change in temperature. The introduction of heat in a body can cause a temperature change or can cause a change in the state of a body. This proportionality sign here will be written as Q equal to Cm delta theta, where C is a constant and it is known as the specific heat capacity. It's written in small letter. Specific heat capacity is the quantity of heat that is required to raise the temperature of a unit mass of a substance such as 1 kilogram through a unit temperature of 1 Kelvin. In specific heat capacity, we are concerned about the mass of a body, which is a unit mass, 1 kilogram, and it is raising the temperature through a unit temperature of 1 Kelvin. Another term we need to take note of here is heat capacity. It is the heat required to raise the temperature of a body through 1 Kelvin. Now here there is no specificity of the mass. The unit of specific heat capacity is joules per kilogram per Kelvin. It may be written as joules per kilogram per Kelvin. While that of heat capacity, the unit is joules per Kelvin. We also have it as specific heat capacity is written as capital C. So we can have it as heat capacity is equal to Cm, where C is the specific heat capacity and M is the mass. The unit of mass we use here is in kilogram. The unit of temperature is in Kelvin. Now what do we use for measuring heat? We can measure the quantity of heat using the mixture method and also the electrical method. Now the mixture method, we use a calorimeter. A calorimeter is a container made of materials such as copper. We use the calorimeter to measure the quantity of heat, and the calorimeter is a container which may be made of copper. It has a thermometer inside it which is used to measure the temperature change. Something about the calorimeter is that it is lagged such that there will be reduction of heat loss, and then we have a stirrer which is inside it. Heat is supplied through a burner, and most especially by introducing hot water or a hot body. This is allowed to mix together until a uniform temperature is achieved. The heat that is supplied will raise the temperature of the material that is inside. We will always consider that in a calorimeter, heat that is supplied or gained equal to heat that is lost by the host substance. Then we'll talk about the electrical method. This can also be measured by supplying heat through an electric coil. The heat that's supplied by an electric coil is measured using this formula, which is I for current, V for voltage, and T for the time. The unit of current here is in ampere, unit of voltage here is in volts, and the unit of time here is in seconds. We ensure that when carrying out calculations under this, they are done in the standard form. So let's look at some questions under specific heat capacity. Question 1. Calculate the heat required to raise the temperature of 10 kg of brass by 10 Kelvin. Here we're asked to calculate the quantity of heat required to raise the temperature of 10 kilograms. So we have it that the formula for quantity of heat equal to mass times the specific heat capacity times the change in temperature. The unit of quantity of heat is in joules. The mass that we are dealing with here is 10 kilograms, and then we are given the specific heat capacity of brass to be 380 joules per kilogram per Kelvin. So we have it as 380 times the change in temperature, which is by 10 Kelvin. So we multiply this through and we have 38,000 joules, which is also 38 kilojoules. Question 2. Find the heat capacity of 5 kilograms of lead, taking the specific heat capacity of lead to be 130 joules per kilogram per Kelvin. Now in this second question, we have to find the heat capacity of 5 kilograms of lead. Heat capacity, which is capital C, is equal to the specific heat capacity multiplied by the mass. Here we have the heat capacity, which is equal to specific heat capacity times mass. The specific heat capacity is 130 joules per kilogram per Kelvin multiplied by the mass, which is 5. So when we multiply this, we have 650 joules of heat, which can be written as 0.65 kilojoules. Kilo is 1000. If you remove this kilo and you replace it with 1000, and if you say 1000 multiplied by 0.65, you get 650. Question 3. A piece of copper weighing 300 grams is heated to 100 degrees Celsius and then quickly transferred to a copper calorimeter of mass 10 grams containing 100 grams of liquid with unknown specific heat capacity. If the final temperature of the mixture is 40 degrees Celsius, calculate the specific heat capacity of the liquid. Room temperature is 10 degrees Celsius and specific heat capacity of copper is 400 joules per kilogram per Kelvin. Here is a quick diagram to illustrate the question. We were told that this copper was heated outside to a temperature of 100 degrees Celsius. And when it was heated, it was quickly transferred into this copper calorimeter. When it was placed into this copper calorimeter containing a liquid, which is here, we were told that the room temperature before this was transferred, the room temperature was 10 degrees Celsius, meaning that the copper calorimeter would have the temperature of the room, likewise the liquid which is inside. But when this copper, which was heated to 100 degrees Celsius, was introduced into the liquid, it's going to lose some heat. Hence, the temperature of this liquid will start increasing gradually depending on the mass of the water and also the mass of the copper calorimeter. So it increases from 10 till it got to 40 degrees Celsius. And at 40 degrees Celsius, the temperature of the mixture, the calorimeter, and this copper will be the same, which is going to be the final temperature. Now heat is supplied by the copper, which is this copper, and the formula for quantity of heat is mass times specific heat capacity times change in temperature. The mass is the mass of this copper. Now the mass of copper that was given in the question is 300 grams, but like we said, we need to work using the standard quantities, and so the mass here, which was 300, we converted into kilogram by dividing the 300 grams by 1000 to get 0.3, and then the 10 grams is converted to kilogram by dividing the 10 by 1000 to get 0.01, and then the 100 grams of this liquid is converted into kilogram by dividing by 1000, and so mass of the copper is 0.3. Specific heat capacity of copper we're given here to be 400. Then change in temperature here was given 100 degrees Celsius, likewise Celsius and Celsius here. Hence we are expected to convert it into Kelvin. But what we are really interested in is the change in temperature. It is not basically the temperature itself. You could convert this into Kelvin, that is, to convert into Kelvin, 100 degrees Celsius plus 273 Kelvin, which is the absolute temperature. So 100 plus 273 will give you 373 Kelvin. Likewise, this will give you 273 plus 1 plus 10, and that will give 283. And you also convert this, but that does not cause a change in the temperature change, and so we could use it in Celsius like that, except when we get to a point where we are to get our answer in Kelvin. So the copper was initially 100 and it's reduced in temperature to become 40. Hence, we'll have it as 0.3 multiplied by 400 multiplied by 60. And so the quantity of heat that was supplied, when we multiply this, we will have 7,200 joules as the quantity of heat which was supplied. Then what about the heat that was gained? Heat was gained by the liquid. So we'll have it as the mass of the liquid, specific heat capacity of the liquid, and the temperature change. The mass of the liquid in the question is 0.1 kilogram. Specific heat capacity of the liquid is unknown, and that is what we are looking for. So we represent it as C. And then the change in temperature. The initial temperature of the liquid was 10 and it increased to 40. So the change in temperature is 40 minus 10, which is 30. So when we multiply this, 30 times 0.1, it leaves us with 3 times C. And then heat was also gained by this container, that's the copper calorimeter. So heat was gained by the calorimeter as well, and that is measured as mass times specific capacity, mass of the copper calorimeter times specific heat capacity of copper times the change in temperature. Now the mass of the copper calorimeter here is 0.01. Specific heat capacity of copper, this and this are made of the same material, so we use the same value, which is 400 times the change in temperature. Temperature change is also the same, so we have it as 30. That is, it was initially this container, the room temperature was 10, and then it increased when this copper ball was put into it, and then it increased to 40. So 40 minus 10 gives us 30. And so when we multiply this, we'll have 120 joules. One thing we should know is that this experiment was conducted such that no other heat was lost. In this experiment, heat that is supplied equal to heat that is gained. So we have it as heat gained equal to heat which is supplied. The heat that is gained from here, we have all this. The unit of this is in joule, and we have this 3C plus 120 equal to the heat which was supplied. The heat supplied here is 7,200 joules. So making 3C the subject of formula, we have 7200 minus 120. That leaves us with 7080 joules. Hence, dividing both sides by 3, we have 7080 over 3. And that leaves us with 2,316 joules per kilogram per Kelvin. And this is the specific heat capacity of the liquid. Alright, so let's look at this example. In an experiment to determine the specific heat capacity of a metal weighing 2 kg, an electric heater was put in a hole in the metal and the thermometer was placed in another hole in the metal. The potential difference across the heater was 8 volts and the current was measured as 6 ampere. If the heater was switched on for 5 minutes and the temperature of the metal rose by 8 degrees, calculate A, the energy supplied to the body, and B, the specific heat capacity of the body. Now this question is an example of measuring the quantity of heat using the electrical method. So in this electrical method, we have seen a heater, that is an electric heater, which was placed inside a metal to increase the temperature of the metal from its initial temperature. Now it increased it to a final temperature, and the change in the temperature is 8 degrees, and that's what we've been given here. So in this question, we've been told to first determine the energy supplied to the body. So energy supplied by the heater here is taken as current times voltage times time, where I is 6, voltage is 8, and time we're given 5 minutes. And because we need to work in the SI unit, we convert it from minutes to seconds. So that's 5 times 60, making 300. So times 300. And so we are left with 14,400 joules of heat that was supplied by the electric heater. Okay, then heat was gained by the metal, and the heat that was gained by the metal is taken as mass of the metal times specific heat capacity of the metal times change in its temperature. The mass of the metal in the question is 2 kg. Specific heat capacity we do not know, so we have it as C. Then the change in temperature is 8. Half 2 times 8 is 16 C, where C is the specific heat capacity. Now we have that heat that was supplied equal to the heat that was gained by the metal without loss of any heat. And so we have 14400 equal to 16 C. Hence, making C the subject of formula, we have 14400 divided by 16, and we'll be left with 900 joules per kilogram per Kelvin. So here is the specific heat capacity of the metal. First question says that we should find the quantity of heat that was supplied, and here we have it as 14,400 joules, which could be taken as 1.44 times 10 raised per 1234 raised per 4 joules, while the C is the specific heat capacity. How many joules of heat are given out when a piece of iron of mass 50 gram and specific heat capacity 460 joules per kilogram per Kelvin cools from 80 degrees Celsius to 20 degrees Celsius? Now this question is quite straightforward. We have to calculate the quantity of heat that was given out when a mass of iron of mass this cools from 80 degrees Celsius to 20 degrees Celsius. So it is possible that the iron itself is the supplier of the heat. They did not tell us where it is supplying the heat to, but we're told that it loses heat. And initially, its initial temperature, which is T1, was 80 degrees Celsius, and its final temperature is 20 degrees Celsius. So changing this to Kelvin may not be needed because all we are interested in is the change in temperature. So the change in the temperature of this question is T2 minus T1, which is 80 minus 20, and that leaves us with 60 degrees. The quantity of heat, which is Q, equal to the mass of the iron times the specific heat capacity of the iron times its temperature change. Now the mass of the iron is 50 gram, and we know that we do not work with gram, so we convert the mass, which is 50 gram, to kilogram. That is 50 divided by 1000, and that leaves us with 0.05 kilogram. So we have 0.05. Specific heat capacity is 460, and the temperature change is 60. And so when we multiply this, we'll have 1380 joules of heat, which could be rewritten as 1.38 times 10 raised per 3 joules, or it could be written as 1.38 kilojoules. Alright, so let's look at this example 6. It says a piece of iron of specific heat capacity 450 joules per kilogram per Kelvin falls through 50 meters from rest. Calculate its rise in temperature, taking G to be equal to 10 meters per second squared. In this question, we have a body that has energy that was lost while falling from rest. So what we'll do is first to calculate the total energy lost on falling from rest. So at rest, the energy that a body possesses, which is called the potential energy, is mgh, where m is mass, g is gravity, and h is the height. In the question, we're not given the mass. That is the energy that was lost. Now the energy that was lost led to a gain in heat. So as it was falling through that height, it was gaining heat energy. So our heat gained equal to mc change in temperature. So heat lost on falling equal to the heat gained. Hence, we have mgh equal to mc change in temperature. The mass here is the same thing as the mass here, so that cancels out. In the question, we are asked to look for the change in temperature. In the question, we are given g to be 10, height equal to 15 meters. We are given the specific heat capacity as to be 450 joules per kilogram per Kelvin, and we are looking for delta H. Alright, so we have our G, which is 10, multiplied by H, which is 15, equal to C, which is specific heat capacity, 450, multiplied by the change in temperature, and that's what we are looking for. And so 10 times 15 gives us 150, equal to 450 change in temperature. We divide both sides by 450. The change in temperature is 1/3, which is same thing as 0.33 Kelvin. This is the temperature change of the body which fell from rest. A car of mass 500 kg moving with a speed of 30 meters per second is brought to rest by applying the brakes. If all the energy is converted into heat at the brake drums, find the rise in temperature if each of the 4 iron drums has a mass of 5 kg. Specific heat capacity of iron equal to 450 joules per kilogram per Kelvin. Here we have a car of mass 500 kg, which is moving at a speed of 30 meters per second and was brought to rest by applying brakes. Now all the energy, that is the kinetic energy, was converted into heat energy at the brake drums. We have to find the rise in temperature. That means when the brake was applied, there was an increase in temperature. At the 4 drums, each drum has a mass of 5 kg. Hence, 4 drums, 5 times 4, and that's 20 kg. And also, we are looking for the change in temperature or the rise in temperature. We have the specific heat capacity of iron to be 450 joules per kilogram per Kelvin. And with this is where heat was gained. So there's a conversion of heat from kinetic energy into heat energy. And so we have that kinetic energy, which is equal to heat energy. Now, kinetic energy is half mv squared as a formula, and heat energy has mc change in temperature. That is how we calculate the quantity of heat. So from here, we have 1/2 times mass is 500, velocity is 30. So we have 30 squared equal to mass of the 4 drums, which is 20, specific heat capacity, which is 450, multiplied by the temperature change. Alright, so we have 250 here. 250 multiplied by 30 squared, that gives us 900, equal to 20 times 450 times change in temperature. So we could make the change in temperature as the subject of formula. Have 250 multiplied by 900 over 20 times 450. Here, this cancels this. 4 here, 1, 4 gives 2. 2 here, we have 10. So change in the temperature equal to 25 degrees. Let's look at some technical questions. 2 liquids, X and Y, having the same mass, are supplied with the same quantity of heat. If the temperature rise in X is twice that of Y, the ratio of specific heat capacity of X to that of Y is dash. Here, we have 2 liquids, X and Y, and they have the same mass. If the temperature rise and they are supplied with the same quantity of heat, meaning Q equal to Q. If the temperature rise in X is twice that of Y, that means the temperature rise in X is 2 times, and then for Y it is still delta theta. Now we are asked to find the ratio of specific heat capacity of X. We are looking for specific heat capacity over here. Now, we have that Q equals to MC change in temperature. And also here, we have Q equal to MC change in temperature. But if you look at this, we have 2 times the delta theta. So we'll have our 2 placed somewhere here. But this is still the same thing. What are we after? We are told that quantity of heat supplied are the same. So we'll equate the 2. So we'll have mass MC change in temperature multiplied by 2 equal to the MC change in temperature. Here, the masses are the same, so they cancel out. The specific heat capacity of X is different from the specific heat capacity of Y. Then we have that our temperature here, delta theta and delta theta will be the same, only that this is times 2. So this can cancel out. We are left with 2Cx equal to Cy. We can put 1 here. So we are asked to look for the ratio of specific heat capacity of X to that of Y. So we are looking for Cx ratio Cy or Cx over Cy. So what we could do is to divide both sides by Cy. So if you divide both sides by Cy, Cy will cancel this. And so we'll have 2Cx Cy equal to 1. And then we'll bring 2 over to this place by dividing both sides by 2. So if we divide both sides by 2, we have Cx over Cy equal to 1 over 2. That is when we bring 2 over to this place. So the ratio of Cx to Cy is equal to 1:2. A block of aluminium is heated electrically by a 25-watt heater. If the temperature rises by 10 degrees Celsius in 5 minutes, the heat capacity of aluminium is dash. Here we have a block of aluminium which is heated electrically by a 25-watt heater. So we have power is 25 watts. If the temperature rises, that's the change in temperature equal to 10 degrees Celsius, and for 5 minutes, the heat capacity, now we are looking for heat capacity, take note, not specific heat capacity of aluminium is what? From this question, we know that heat capacity equal to specific heat capacity times mass of the aluminium. Then from the question, we're given power and we're given time. So from here we can calculate the quantity of heat that was supplied. Heat supplied equal to PT. P can also be said to be IV, that is current times voltage. The power over here is 25 and the time is 5 minutes. But we need to convert the 5 minutes into seconds by multiplying by 60. And so we have 300. So 25 times 300, that gives 7,500 joules. So here is the quantity of heat that was supplied. Heat gained equal to MC change in temperature, where this C is the specific heat capacity. And here we have the mass. Don't forget, what we are looking for is the heat capacity, not the specific heat capacity. So what we could do is, we know that this C here is not what we are looking for, and we know that C equal to the small c equal to. So here is the heat capacity. We'll take this one as the heat capacity. From here, we could make the specific heat capacity as the subject by saying the small c equal to heat capacity over m. Now let's substitute that into this equation, and we'll have heat gained equal to m times the heat capacity over m times the change in temperature. So heat gained equal to H times the change in temperature here is 10. So we have it that heat gained equal to heat supplied. We know that heat gained is heat supplied, and so we could substitute heat supplied here, and the heat supplied is 7,500 equal to the heat capacity times 10. Hence, heat capacity equal to 7,500 divided by 10. And so we have 750 joules per Kelvin. That is the heat capacity. Alright, so let's look at this question. It says A 50 watt electric heater is used to heat a metal block of mass 5 kg. If in 10 minutes a temperature rise of 12 degrees Celsius is achieved, the specific heat capacity of the metal is dash. Now in this question, the power supplied by the electric heater is 50 watts and it is used to heat a metal block of mass 5 kg, and that was carried out in 10 minutes. A temperature rise of 12 degrees Celsius. We are looking for the specific heat capacity of the metal. First, we convert the 10 minutes to seconds, which is 600 seconds. Then we have that heat supplied by the electric heater is equal to heat gained by the metal. Heat supplied is taken as IVT, and then heat gained by the metal is MC, change in temperature. Now, where IV is the same thing as power, this is power. We substitute with this power, which is 50 multiplied by time, which is 600, equal to mass of the metal, which is 5, specific heat capacity is unknown, change in temperature is 12. And so we'll make C the subject of this equation, and we'll have 50 times 600 divided by 5 times 12. 5 here, we have 10, 12 into this, so we have 10 multiplied by 50, that's 500. Hence, the specific heat capacity of the metal equals to 500 joules per kilogram per Kelvin. The temperature change when 500 joules of heat is supplied to 100 grams of water. This is quite straightforward. We are told that heat supplied equal to 500 joules, and then heat is absorbed or gained, which is MC, change in temperature. So it was gained by the water. The mass of the water which was given is 100 grams. So mass of water is 100 grams, which we will convert into kilogram, and that will give us 0.1 kilogram. So we have 0.1 kilogram, and then the specific heat capacity of water, which is 4,200, and we are looking for the temperature change. This 0.1 multiplied by 4,200 will leave us with 420 delta theta. Knowing that heat supplied equal to heat gained, hence we have 500 equal to 420 delta theta. Making delta theta the subject of formula, or we'll divide both sides by 420. So we have 500 over 420. We'll be left with 1.2 degrees as the temperature change. In this next question, we're told that an immersion heater rated 2.0 ampere and 240 volts is used to boil water from temperature 52 degrees Celsius to 100 degrees Celsius. If the mass of the water is 2.5 kilogram, determine the time taken to boil the water. Here we have a heater which has a current of 2.0 ampere, has a voltage of 240 volts, and it was used to supply heat to boil water, which has an initial temperature of 52 degrees Celsius and a final temperature of 100 degrees Celsius. We're told that the mass of water which is boiled was 2.5 kilogram. We are looking for the time taken to carry out this operation. Knowing that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Heat supplied by the heater equal to heat gained by water, which is IVT equal to MC, change in temperature. We are giving I to be 2 and V to be 240 times the time, and the mass is 2.5. Specific heat capacity is 4,200, and we're told that the temperature change is from 52 to 100, so we have 100 minus 52. So 2 times 240 gives 480 T. 2.5 times, so we have 2.5 times 4200 times 100 minus 52 leaves us with 48. We'll make T the subject, and we'll have 2.5 times 4200 times 48 over 480, and that will leave us with 1050 seconds, which could be written as 1.05 times 10 raised power 123, that is raised power 3 seconds.